Welcome, everyone, to the Topological Complexity Seminar. Today, our speaker is Arturo Espinosa Baro, and he from Adam Mickiewicz University, and he will speak to us on properties of effective topological complexity and effective LS category. Take it away, Arturo.
First of all, thank you very much to the organizer for inviting me to present this topic at the seminar. So I'm going to talk about this recent work that this was made in jointly with Zbigniew, Błaszczyk, and Viruel about these properties of effective topological complexity and effective LS category. I will make like a small presentation, very, very briefly, of different equivariant notions of topological complexity before we specialize to the case of effective TC. And then I will go a bit through the details of the work we made, and I will finish with some considerations about future lines and some other stuff that I think could be interesting to consider for the future. So first is the mandatory introduction on the motivation about topological complexity, which maybe is not really so needed in a context like this. But okay, so I am covering my whole screen, actually. Wait. Okay, so for the motion planning problem of mechanical system, we say we mean essentially, yes, we mean essentially the finding an algorithm which is instructing us how to move from two different states of our mechanical system or robot, understood in a broad sense as some sort of automatic processes with different set of states which are going to form what is called the configuration space. So we want to produce this algorithm instructing how to move from state X to state Y, and this algorithm is precisely what it is called the motion planner, which is given any pair of points, and this algorithm outputs a path that is joining these two states, that is instructing us how to move from one state to another. So okay, so to formalize it mathematically, we consider the Serre path space vibration, which is defined from the free path space to the Cartesian product of X with itself, just taking one path and evaluating to the extreme points, to start point and end point. And then we can say that the motion planning algorithm can be described as a map, which is going from X time X to the path space, and such that the composition with the Serre vibration is given the identity. That is, motion planning algorithm can be understood as a section of the path space vibration. And there, Farber introduced the notion of topological complexity as a way to study the instability of the motion planning problem, because in general, such a section can only, such a continuous section of the whole space will be only possible for the case that the space is contractible. So in order to study this instability, it was introduced the notion of topological complexity, which is the least integers greater or equal to 0, that's such that they exist. I have to establish since the beginning that I am all the time working with a normalized notion of topological complexity, because I want the topological complexity of contractible spaces to be 0, not 1. So just recall that the original, this whole, I mean, if you compare with the original paper on effective topological complexity by Błaszczyk and Kaluba, they are all the time working in the original notion of TC. Just have to adjust by one unit. So as the topological complexity is the least integers such that there exists an open cover of X time X by K plus 1 open subsets, satisfying that over each one of those open subsets there exists a local section of the path space vibration. So the whole notion of TC and also of the Lusternik-Schnirelmann category are specific cases of the broader notion of sectional category. Here I recall the definition of sectional category of a map. In general, we are not going to use so much of arbitrary maps. We are specializing on vibrations. So the sectional category of a map is the smallest integer such that there is open cover of the codomain and continuous maps with the property that the composition of continuous map over each of those open sets, the property that the composition is homotopic to the inclusion. Recall that if we are working with explicit fibrations, this condition that these homotopy conditions, I mean that those maps are local homotopy sections of the map are not can be just considered as straight up local fibrations. I mean that the composition is not, instead of homotopic, is just the identity restricted to the open subset. And of course we recast the notions of LS category and topological complexity in terms of sectional category, because we are going to use actively all sectional category and the properties of sectional category in order to establish the main notions in effective topological complexity and in order to derive properties. So if we consider the fibration, which is the evaluation of the path in the endpoint, then the sectional category of this evaluation fibration becomes the famous Lusternik-Schnirelmann category. And of course, if we are just considering the Seg path space fibration, then the sectional category of this fibration, it's immediate to see from the definition that coincides with the topological complexity of the space X. So as I was mentioning, I have to recall some properties of sectional category, because we will be mentioning several of them in the. I mean, we will be making use of several of them in what comes next. So if we have a fibration, we have the well-known upper bound of sectional category in terms of the Lusternik-Schnirelmann category of the base. Then we have the classic cohomological lower bound of sectional category, which becomes the nilpotency of the kernel lower bound in terms of topological complexity. This I will put also on the I will reflect in the next slide. So we have k. I mean, we have the maximum integers that exist k cohomology classes in the kernel of the homomorphism at the level of cohomology induced by the fibration, such that the cap product is different from zero. And we have that the sectional category of the fibration is greater or equal than this k. Then if we have a fibration and we take any map from space X to the base, and if we consider the pullback of the fibration over this map, then we have that the sectional category of this pullback fibration is less or equal than the sectional category of the original fibration. And moreover, if this map through which we are pulling back is indeed a homotopy equivalence, and we have that the two sectional categories coincide, and this is this allows us to show also that the notion of topological complexity is indeed a homotopy invariant of the space. So now if we have two fibrations and we consider the products, we have the also well-known upper bound in terms of the upper bound of the product in terms of the sum of each of the components. So we have the sectional category of the product fibration is lesser or equal than the sum of the sectional category of the factors, and the dimensional upper bound, which will appear also towards the end of the presentation. We have the dimension of the basis D, and that the fiber is S-1 connected. Then we have that the sectional category of the fibration is strictly lesser than the dimension plus 1 over connectivity plus 1. So those properties of sectional category specialize for the case of TC in the very well-known bounds. For example, in terms of Lusternik-Schnirelmann category, that TC is bounded from below by category and from above by category of the product, less or equal than twice the category. And this is the upper dimensional upper dimensional bound for topological complexity, which is the last point that we were mentioning in our properties of SECAT. If we have an S-1 connected space, and we have that the category of the space is less or equal than the dimension of X over S, and the topological complexity is less or equal than twice the dimension of X over S. And in particular, of course, if X is path connected, then we have the categories less or equal than the dimension, and topological complexity is less or equal than twice the dimension. And the cohomological hour bounds for sectional category specialize in the cases of category and TC in the famous cap length for category and nilpotency of the kernel of the diagonal inclusion for topological complexity. So now we can go to introduce the ideas that are the most prevalent. I mean the most fundamental ideas on this talk about the equivariant notions of topological complexity. It's it can be quite common actually that the configuration space of our mechanical system comes equipped with some sort of symmetry. Symmetry here is understood, of course, as an action of a group on the space. I mean, the most natural example that always comes to mind is this robotical arm, right? And you are allowing to move toward you are allowing it's working on a plane, but you are allowing to you are giving it additional degrees of freedom by allowing to move longitudinally from the plane, right? Towards around fits joint at the base. So of course it comes natural that if we are allowing, I mean, if we are in presence of these symmetries in our configuration space, we might want to recover this kind of information in our in the study of the complexity of the motion planning problem. The original notion of topological complexity is not taking into account this kind of phenomenon. So arise the need to consider some broadly understood equivariant notions, because each of them, of course, has a different, it's reflecting different kind of information about the symmetries that appear. So the most natural is the first one to appear was the equivariant topological complexity, introduced by Coleman and Grant in 2012. The equivariant topological complexity is indeed the natural in the sense that it's asking for the motion planners to be equivariant in the sense that as here on the definition, the sections, the local sections that you are considering for your path space vibration, which is here is a barrier. Here is this evaluation is a variation of the path space vibration when we are considering the diagonal action of G over the product. So these local sections of our vibration, we want them to be G equivariant maps that are making this sort of diagonal commutative. So sorry. So this is essentially meaning that when we are making the motion planner between these two states that are joined by this action of the group is the same as we want this to be preserved by the group acting on this space, right? So a variation of the equivariant topological complexity from Coleman and Grant is a strongly equivariant topological complexity from Zbigniew, introduced in 2015. This is, instead of considering the diagonal action of G over the product, here Zbigniew was considering a G times G action on the product, and here the sections are this G times G equivariant local section making this diagram commutative. This was introduced in order to provide better upper estimates for the original topological complexity, because this actually one of the properties of equivariant topological complexity is bounding from above the original topological complexity is always greater or equal than the original topological complexity. This fact that is always greater or equal than the original TC it's actually opens up for the consideration if it is possible to use these symmetries not only to introduce this natural notion of equivariant motion planners, but to try to reduce the complexity of the motion planning itself. one of the phenomena that appear in precisely in this that allows for the equivariant topological complexity to be greater than the usual TC is that it is taking into consideration the diagonal action of G on the product, where topological complexity of the quotient should be taken should be regarded into over the product of the quotient spaces. So in order to study in order to define a natural notion of G times G equivariance for the topological complexity, Błaszczyk and Martentowicz considered the following replacement for the path spaces. This is a natural projection map defined over this replacement, which is taken to the, of course, to these two paths alpha and beta are taken to alpha evaluated on the origin and beta evaluated on the ending of the path, and this is a G times G fibration under the component-wise actions. So the sectional category, I mean, no, sorry, the natural topological complexity that associated to this notion is what is to this replacement. Sorry, is what we are calling invariant topological complexity. That is by Błaszczyk and Martentowicz in the 14. Invariant topological complexity we are requiring for this this natural projection map a set of G times G invariant sets on the space on the product of X with itself, and G times G equivariant local sections to this replacement of path spaces of our natural projection map defined like this, and make this diagram commutative. And for the sake of completeness on the presentation, I will also introduce very briefly these other two more recent notions of equivariant topological complexity, which is the effectual topological complexity and the orbital effectual topological complexity. The first one introduced by David Aguilar, González, Gutiérrez, and Ipanarque Zapata in 2021, which can be defined as the sectional category of this composite map, and which in most of the interesting cases it coincides with the topological complexity in the sense of pavesage of the orbit projection map. And this orbital topological complexity by Balzer and Torres-Giese in 2021 as well, which is defined as a sectional category of the composition of this of the usual path space vibration precisely with the orbit projection map. Those two notions have been used precisely to study related to effective topological complexity in order to study some relationship between these notions and effective TC, and to provide some examples of motion planner of actual motion planners on different spaces for effective TC and for effectual and for orbital TC. So now we are entering finally into the effective topological complexity. So what's the big motivation of effective topological complexity, as I was mentioning before, is that the natural notions of equivariant topological complexity are not actually taking into account that the complexity of the motion that you might want to truly reduce the complexity of the motion planning, in the sense that it's in the presence of symmetries, in the sense that you are using the symmetries to identify points in your configuration system that, even if they are physically different, are functionally equivalent, right? For example, consider this example of this robot arm that is we are allowing to a movement, a rotation on the wrist. Those two states, because we are not making difference on the end plier, so these two states are physically different, so they correspond to two different points on the configuration space, but they are functionally equivalent because those two grips are indistinguishable, right? So what we want is a motion planner that is arriving to this a motion planning that is taking into consideration these jumps with symmetry, that it's arriving to this it's arriving to a possible state, then it's reevaluating by a jump, by some series of jumps prescribed by the symmetry on the system, and it's identifying these functionally equivalent states in order to not make unnecessary navigations inside the system. So, in order to reflect that, Błaszczyk and Kaluba introduced the notion of broken path spaces. This is a collection of paths such that the orbits of the endpoint of one path is coincide with the orbit of the beginning of the next path. So here we have those prescribed jumps between functionally equivalent points in our configuration system. In particular, in stage 1, this broken path space recovered the usual path space. In stage 2, recovered this replacement that Błaszczyk and Martentowicz were suggesting. And we have the K effective path space vibration, which is taking this broken path and evaluating the first path on the beginning and the end, and the last path on the ending. Notice that given that we are taking sorry, this I should mention in a moment. First, the saturated diagonal of X is defined as this expansion of this dilation of the diagonal by the action of the usual diagonal by the action of the group. And we can see that actually this effective path space vibration is a vibration that we can recover precisely by composing in this diagram that I'm showing here, composing this this PK natural projection, the first and last, this PK, sorry, projection with the composing with the projection onto the first and the last factor. This is indeed a pullback diagram. So now the case stage effective topological complexity. First, we define a GK motion planner as an open subset with a continuous local section of the K effective path space vibration over the open subset. And the K stage effective topological complexity is the smallest integer such that there exists an open cover of X times X by these n+1 sets admitting GK motion planners. Equivalently, we are defining the effective topological complexity of the sectional category of this effective path space vibration. Notice that given that we are requiring that it is only the sectional category of this vibration, this effective topological complexity is not the local sections are indeed not equivariant. So this effective topological complexity is equivariant in this the only equivariant part of this effective topological complexity is actually that the information of the symmetries is inside the path space. It's telling us how we are navigating from points that are related by the action of the group, but the TC itself is not is working very differently from the rest of the equivariantly defined topological complexities, and this will give a lot of complexity to several of the situations that can be found in effective topological complexity. So in particular, the first stage of effective TC coincides with the original notion of topological complexity. So some interesting properties of these effective topological complexities proved in the original paper by Błaszczyk and Kaluba is that these K-stage effective TCs are actually less or equal when we are considering subgroups inside when we are considering the action of subgroups. These K-stage effective TC are forming a descending chain of category-like invariants. And if there exists a map between the spaces X and Y and a map in reverse such that the composition is homotopy to the identity on Y, then we have that the K-stage effective TC of Y is less or equal than the K-effective TC of X, and in particular, if both of them are geomotopically, X and Y are geomotopically equivalent, then we have the equality between the K effective topological complexities. And the effective TC is defined precisely as the minimal integer such that this descending chain stabilizes for every integer every integer from that point onwards. We define the topological complexity, the effective topological complexity. You can think that the effective topological complexity is the minimum of the k-stage effective topological complexities, because from one point onwards it's stabilizing and keeping constant. And one of the main works in one of the main results in the original paper of Błaszczyk and Kaluba is precisely the computation of the effective TC of the set P spheres. When we are considering P prime, of course, and set P acting on Sn, if P is greater than 2, then the effective TC coincides with the usual TC of the sphere. But if the interesting case comes when the P is equal to 2, then the effective TC of the sphere depends on dimension of the fixed point set R, as it is present in the following table. So we introduced now I finally jumped to what we were introducing into recent our recent work. We introduced the notion of the global effective path space because you can immediately consider this an inclusion of the broken path spaces of broken path space of the stage K into the stage K plus 1. These inclusions embed these broken path spaces as a closed subspaces of the next one. And of course, you can define the global effective path space as the colimit with respect to this chain of inclusions, and endowed with the final or the colimit topology. Okay, so now if you are considering G product of G times K times with itself on the broken path space, you can construct, by acting on each of the components and then go into the quotient by the action and concatenating paths there, you can construct the following commutative diagram. And if there is a section of this map rho K in this diagram, then we have our first result on our first new bound in terms of our first new bound, sorry, of effective topological complexity. Now in terms of the topological complexity of the quotient space, we will see the quotient space with respect to the group action, of course. We will see again that the TC of the quotient space will appear several times later on. Before continuing, I should probably mention that there is also there is another variant of effective topological complexity already defined. I will very quickly introduce it. We can define a variant of the K-broken path space. Like this is a subspace of tuples with this prescribed element of the group that is linking at stream of one point to the beginning of the next one. And you can define this G-twisted evaluation map, which is essentially the same as the evaluation map as the effective vibration path space, but with a different, of course, a different domain this time. Using this substitution of the broken path spaces, Calavita Aguilar, González, Gutiérrez, and Ipanaque Zapata in 21 defined this alternative notion of effective topological complexity as the sectional category of this G-twisted evaluation map. The interesting point of this variant of effective topological complexity is that it's actually stabilizing from point 2 onwards, and it's coinciding with the effective topological complexity with the original effective topological complexity for nice enough group actions and nice enough spaces, and it's in general it's acting as an upper bound of the original effective TC. It is conceptually it's behaving much more nicely than the original effective TC, but the main issue it has is it's not actually reduced. It's not actually carrying all the way the original intention of effective TC in reducing as much as possible the complexity of the motion plan in terms of the symmetry, right? And I will end at the end of the talk. I will give an example, or a very simple example of a sequence of TC that is actually going lower, very explicit from 2. On the stages. I mean. So, okay, the notion of the effective LS category. Why we want a notion of effective Lusternik-Schnirelmann category? There is a notion already of equivariant Lusternik-Schnirelmann category. We say that G invariant open subset is G categorical if the inclusion is G homotopy to a G equivariant map with values in a single orbit. Using this idea, we can define the equivariant LS category or LSG category of X as the smallest integer such that there exists an open cover of X by n+1 open subsets which are G categorical. And of course, one immediately wonders if it is possible to have the usual bound, the relationship between this equivariant LS category and equivariant notions of topological complexity, mimicking how the usual LS category relates to the usual TC, right? So if X is G connect, the results I'm presenting now were proven by Coleman and Grant and by Błaszczyk and Kaluba. If X is G connected, then we have that the equivariant TC of X is less or equal to this LSG category. And if X is completely normal, G connected and with at least some fixed point set, then the category, then we have the usual lower and upper bound of equivariant TC in terms of equivariant LS category, LSG category. And if X has a fixed point, then the invariant topological complexity is greater or equal to the category of the LSG category of X. So the question is how it would be. It is actually possible to do something like this, to give some variation of the lower of the bounds in terms of LS category for effective TC. Błaszczyk and Kaluba showed that no such lower bound is possible for TC, and actually the impossibility is not merely conjunctural, but it's coming from the philosophy behind invariant. That is, this kind of bound that we are striving for will be impossible to accomplish for any other homotopy invariant, like called mathcal TC, with the property that it is less or equal to the effective topological complexity. So we need, in order to find the analog of our LS category, we need of classic LS category, we need to introduce a new notion of LS category, which is the effective Lusternik-Schnirelmann category. And again, this is not so surprising when you are taking into consideration that unlike all the other notions of equivariant of equivariant topological complexities, this effective TC is not equivariant all the way down, as I was mentioning. We are requesting that the local sections have not really equivariant maps. So for the usual path space vibration, we can see the relationship between we can encode the relationship between LS category and TC in this sort of pullback diagram. So we now seeing that we can just see the original path space vibration as the P1 for our effective path space vibrations. We just construct an analog of this pullback diagram. We have here another pullback diagram, and we construct this QK vibrations as a pullback by this diagram of the effective path space vibrations. This way we obtain these pullback vibrations, pullbacking back through the inclusion, and then we can define the effective Lusternik-Schnirelmann category as the sectional category of these QK vibrations, and the effective LS category as the minimal of these, because they are forming also a descending chain, a descending chain of integers. Then, as I was just mentioning, in analogy with the effective topological complexity case, we have that the effective LS category is less or equal than the K stage LS category, and this is also less or equal than the original category of X. And then we produce we generalize to the contents of the effective TC and LS cut the category bounds from the classical category bounds. So we have this chain of inequalities. The effective TC is bounded from below by the effective LS category, and from above by twice the effective LS category. I mean, most of these inequalities are coming from straight from properties of the cut. So the truly interesting case is why TC is less or equal than the category of the product, and this you can see by taking when you are taking a cover of X times X for a categorical cover for QK, and you are defining this section. You are having this map, and you can define the local sections by the next definition, where here -1 is taking the paths in the reverse side, and by this asterisk here we mean concatenation of paths. This is determining a local section of the 2K-1 stage effective path space aberration. Hence we have that the effective TC is bounded from above by the effective Lusternik-Schnirelmann category of the product. As a corollary of this, actually, we can make a straight up computation of the effective LS category of the spheres. It's not so surprising that actually all of them are going to coincide with the usual at one with the usual Lusternik-Schnirelmann category of the spheres. And we can also wonder what is the relationship of this effective notion of LS category with the category of the orbit projection map. So recall that we say that the LS category of a map is the minimal number of open sets, so that this is the map is null homotopy over each one of them. So we have actually not so surprisingly that the LS category of the orbit projection map is a lower bound for the LS effective Lusternik-Schnirelmann category of X. This we can see. I mean, if we construct the following map from the broken path space to the based path space on the quotient, which is essentially taking each of the components on the base broken path space, taking them down using the orbit projection map, and then concatenating the resulting paths on the quotient. We can define if we take an open cover for the effective LS category of X with local sections for QK, we can define such we can define family of homotopies like this, and from here we can see that indeed what we are saying is that over this categorical cover for QK, the orbit projection map is null homotopy. As an example, we can make a bound. Perhaps it should be going a bit quicker. So here we can using this, for example, we can make some sample of computation on how we can bound the effective topological complexity of the product of complex projective spaces with set 2 acting by switching of coordinates. The bound that this is the bound that the LS category of the map is bounded from below by the nilpotency of the image is coming from the classic properties of LS category, and then we are just using precisely the full knowledge of the structure of the ring structure of the homology of of the complex projective space. Here, X and Y are taken as the generators of the degree 2 cohomology of the complex projective space, and each of the factors of the product. We have that the DC of this product with this set to action is greater or equal on the LS category of with this same action on this product, and this is greater or equal on the category of the orbit map projection, and this is greater or equal to n because of the new potency of the image. So one of the significant open problems right now in effective topological complexity is determining when effective for which spaces and actions the effective topological complexity is equal to 0. So for the usual topological complexity, as I was mentioning in the beginning, TC of X is 0 if and only if X is a contractible space. We have from the original paper and straight up from the definition that if X is a contractible or a G-contractible space, then the effective topological complexity of X is immediately seen to be 0. But the converse is not true. And a very easy counterexample comes precisely from the computation of the effective TC of spheres. If we are taking Z2 acting on Sn by involution interchanging the two hemispheres and leaving the equator, we can just go to the computation of effective TC of the spheres and see that this effective topological complexity is equal to 0. So, okay, what about imposing some conditions on the orbit projection map? So imagine that we have a G space such that the effective TC of X is 0. Then we can find that the orbit projection map has to be null homotopy. And the question is this condition strong enough? I mean, it will be possible to state to prove the converse. As I was making a spoiler a moment ago, once again, the converse is not true. And a counterexample this time is more elaborated, but it's also using the bedrock of the computation on the spheres. Now this time consider a 6-dimensional sphere with Z2 acting on it via the usual antipodal action. And the orbit projection map, take the orbit projection map, and then you can make the suspension of the orbit projection map. So we are taking the 8th suspension of the orbit projection map coming from the antipodal action of Sn, and this can be seen to be null homotopy. Actually, by the work of Ries in the 1969, the orbit projection of Sn to RRPSN is stably trivial for n equal to n seats. So this map can be seen to be null homotopy, but this 8th projection of the S-seat sphere equipped with the corresponding involution that is inheriting from the involution of Z2 on Sn has a 7-dimensional fixed point set. So then again, if we are going to the computation of the effective TC of the ZP spheres, we see that this effective TC is actually 1, even though the orbit map is null homotopy. So, okay, the question is still open, and then I will come back to this. I mean, I will mention it again when I'm opening. When I will be talking about interesting topics to investigate on the matter. But perhaps we can have some help from LS category, because from the bound of topological from the relationship that we exhibited before on topological complexity and LS category, we can see that for a G space, it is equivalent to require that the effective topological complexity is equal to 0 and the effective LS category is equal to 0. So perhaps the investigation of the effective LS category will prove to be at least a bit easier than in the effective TC case. Okay, so now that we were seeing some conditions on the orbit projection map, we want to investigate the relationship between the topological complexity and the orbit map. The orbit map encodes a lot of information about the precise action on the group. So We will distinguish here two possible cases. The first one is when there is a strict section from our orbit projection map. If under this situation we have that the LS category, effective LS category coincide with the category of the quotient, and the effective TC coincide with the topological complexity of the quotient. Very, very roughly an idea of the proof. Okay, so we start from I mean, both are quite to prove both the statement is quite similar. So I'm going to mention only for topological complexity. Of course, what we want is to make a constant use of the fact that we have a strict section from the orbit from our orbit projection map, right? So we start with open cover for TC on the quotient and its local sections. We define these candidates of open cover of effective open cover as a pre-image by the orbit projection map, and we consider the following map induced by the strict section on the orbit projection map. Using this map, this map, we can define local sections at stage 3 by the following one. We are putting the constant map at the endpoints, and then we are plugging inside the image through this this map induced by the section of those local sections over the local sections with respect to TC of the in the quotient. From here we can see that the topological complexity, the effective topological complexity, this is indeed an effective cover for the effective path space vibration at stage 3. So it's the effective topological complexity is less or equal to the TC on the quotient. And to see the reverse inequality, we take our open cover with local sections for the K stage effective topological complexity. We define this map induced by the orbit projection map, which is essentially evaluating at each of the points of the at each of the components of the broken path space. We are taking the paths and we are passing to the quotient via the orbit projection map, and then we are concatenating the resulting paths there. And then the map defined as such, as the composition of this map with the local sections, and then the strict section, each of the components define a local section for the path space vibration over the quotient. So we have the reverse inequality, and we have the equality. And the idea for, I mean, of course, the technicalities are varying a bit, but the idea for effective LS category is essentially the same. You can consult in our work. Okay, so we have plenty of examples on how to use this result. For example, the unitary group, we know that fits inside this short subsequent only groups. So the effective topological complexity of SUN acting over the unitary group coincides with the topological complexity of S1, which is 1. In general, we for a rich source of examples on how to use this property, we can go to split Lie group extensions. Like here, I give one of such examples. If we are taking a P prime strictly greater than 2, we can define this group as the product of SOPR with itself over the fiber product over the diagonal cyclic subgroup of the center of order PR. Then this is acting on this product by left action on just the first coordinate, and then we obtain, using precisely this action, we obtain this exact sequence with global. I mean this group extension with global section. So the effective topological complexity of SUPR over this SPR PR coincides with the category of PU PR, and this is 3 times PR minus 1, where this last inequality was computed by Nishimoto, Mimura, and sorry for the name of the first author that slips from my mind right now. Sorry, sorry, it slipped from my mind. Tanaka, sorry. Tanaka, Nishimoto, and Mimura, sorry. Okay. So perhaps more way simpler, but more interestingly, because it will allow us to give a realization result for effective topological complexity, is that we consider a base space and G any group, and we construct a wedge with an action wedge that is entries of the base space indexed by the elements of the group, and with an action that is essentially changing. Then we have the topological complexity of this wedge space coincides with the topological complexity of each of its component on the wedge, and this allows, as I was mentioning, to give a realization of the topological complexity of X. We consider any group and then a non-negative integer. We take a G space X such that we have that there exists a G space X such that the effective TC of X coincides with N, and essentially we take Y with fits topological complexity at N, and then we construct this wedge of Y indexed by the group in the manner that we just described. It's very simple result, but nonetheless it's interesting to see that we can actually make this realization. So now we consider the other case that we were mentioning, where the other map is a fibration. Here the situation is a bit it's also quite nice, but just slightly more complicated in that we don't have the equality, but we have the upper bound of in terms of the category and the topological complexity of the quotient space. But nevertheless, we know that both effective LS category and effective TC stabilize at 2. Okay, I have to be a bit quicker because I see I'm going a bit slow. So the idea that we want to use through the main idea of the proof here is all the time going to the quotient and considering paths on the quotient as homotopies on the quotient, and then lifting them precisely by the homotopy lifting property of the fibration. I'm not going to enter too much into the details on the proof here. You can consult on the paper that is in the archive. But as I mentioned, this is essentially the idea exploiting the homotopy lifting properties regarding paths on the quotient as families of homotopies, and then lifting them to. Okay, so here I put a lot of. I wanted to more or less describe the idea of the proof, but I see I'm quite short on time, so you will excuse me. I will skip the idea here on the proof. Okay, so I will go straight to applications of this result. First, I have to notice that Cadariza, Aguilar, González, Gutiérrez, and Ipanaque Zapata had a variation on this. On a similar result, in that when X is Hausdorff and G is discrete and acting properly and discontinuously on X, and we have that the effective TC is less or equal than the effectual topological complexity, and this is less or equal than the topological complexity of the quotient. So here we have generalized to broader class of group actions. So in particular, all the interesting examples that are not covered by this previous result are going to be with topological non-discrete groups. So for example, we have very simple computation, the matrix Lie groups utilized in this result. I mean, matrix Lie group in the sense that it's a matrix Lie group with action of a subgroup, which is the same kind of matrix Lie group on dimension 1 minus 1. Here we have for the SON, for the unitary group, for SU, or for the symplectic groups. And we have also for estimation, I mean, upper bounds of the orthogonal actions of the Stiefel manifolds. This way is using the result that we just introduced and taking the computation of the topological complexity of Grassmannians that was carried out by Petar Padesic. And also it's possible to find interesting applications for group actions on manifolds. We are taking an n-dimensional oriented Riemann manifold. We can define the frame bundle, the set of orthonormal, the frame bundle, bundle of positive orthonormal frames on the manifold. So for the case of frame bundles, we have that if M is path connected and dimensional and smooth manifolds, and we are considering this SON bundle, orthonormal frame bundle, the topological complexity of the SON action of the frame bundle is less or equal than twice the dimension. This comes precisely from the upper dimensional bound on topological complexity that we saw at the beginning, and our result on of the orbit projection map being a fibration. And furthermore, if M is parallelizable, then the orbit projection map actually has a strict section. So the effective TC in this case will coincide with the topological complexity of the manifold itself. Another interesting example is, for example, smooth free proper actions on smooth manifolds. We take a Lie group acting smoothly, freely, and properly on a connected smooth manifold M. We have that the effective TC of the manifold is less or equal than twice the dimension of M minus the dimension of the group. Why is this? By the quotient manifold theorem, the quotient under this hypothesis, the quotient is a manifold, and the dimension of this quotient coincides with the dimension of M minus the dimension of G. And this has quotient manifold has a unique smooth structure, which is making the orbit projection a smooth submersion. Then we just have to use Ehresmann fibration theorem. This becomes a locally trivial fibration, so we can apply our result, and we have by the upper dimensional bound on topological complexity that this effective TC here is bounded from above by twice this dimension. Couple of consequences, and I changed to to different thing. So for a group, for a group G, if we have a G space with orbit base point contractible, then the effective category will coincide with the category, with the usual category F. And if we have a finite group and a free G space such that the category and the topological complexity coincide, then the effective topological complexity can be seen as the usual Lusternik-Schnirelmann category. As an example of this, we have a connected Lie group, then further prove that the TC of the group coincides with the category. So if there is a finite non-trivial discrete subgroup, then the effective TC with respect to this subgroup, with respect to the action of this subgroup, coincides with the category of G. For example, for G non-nilpotent simply connected groups, there is always this kind of subgroup. And Lupton and Scherer showed this coincidence if X is a connected CWH space. So if the group is finite and is acting freely, we have also that the effective TC coincides with the usual category. And for the case of the torus, if we have a finite group acting freely on the torus, then the TC of the torus coincides with the order of it, with the dimension of this. With the order of the torus. I would like to point out that those bounds are not necessarily sharp. For example, if we identify S1 with the unitary group, we know that we can consider this sequence, and as such, the topological complexity with respect of the S1 acting as a unitary group on S2n minus 2n plus 1 is less or equal to the topological complexity of the complex projective space, but this bound here is not sharp because we can consider set P as a subgroup of S1. So we can just go to the computation of the effective TC of set P spheres and see that it's actually one. And also by the I mean, it's less or equal than 1, and it's a 1 by the null homotopy condition that we just described. Okay, so very quickly, just I will just state our dimensional conditions to see when the topological complexity at stage 2 is strictly greater than 0. This part from the idea that the saturated diagonal can be represented as moving all the saturation on the first component via this identification. So we can decompose the saturated diagonal into this union of slices in terms of the elements of the group G. And there is actually a homotopy equivalence between the broken path space at stage 2 and the saturated diagonal. This is generalized in the homotopy equivalence that was noted before by Calvita, Aguilar, and Gonzalez, but only for finite free actions. And here we are generalizing to arbitrary ones. Now we are restricting to finite groups, not necessarily free actions, but here we have a technical lemma bounding the dimensions of the union of fixed point sets in terms of the dimension of the space and cardinality of non-trivial subgroups or list of non-trivial subgroups of G. This is just a technical lemma for the following theorem. We have a GCW complex such that here I'm all the time putting the cohomological dimension, but I mean you can just put dimension. This is a sense that greater degree in cohomology that is non-trivial. The cohomological dimension of the dimension of the fixed point set is less or equal to the dimension of the space for non-trivial subgroups. Then for any list of elements of G, we have this this upper bound for the dimension of the saturated diagonal with respect to this list. And in particular, we have that the dimension of the saturated diagonal is less or equal to the dimension of the space plus the order of the group minus 1. This is proved by induction on the length, and actually using a Meyer-Vietory sort of argument on the saturated diagonal. That's essentially from considering this from building these spaces, we are in the situation because we are all the time in as I mentioned at the moment ago, that we are in compact G, A, and R. So the saturated diagonal is a G times G compact A and R. So we can use a closed version for Meyer-Vietory's theorem. So all the conditions are satisfied. We just derive this upper bound. And we use this to give the condition of non-vanishing for the effective topological complexity at stage 2. Under the assumption of the theorem, we have that if the order of the group is less or equal than the dimension of the space, then the effective TC is strictly greater than 0. This is precisely because we are the map. I mean the fibration, the effective fibration is induced in map in cohomology, which by the homotopy equivalence we can substitute the second broken path space for the saturated diagonal, and then we know that the cohomology on the cohomology of the saturated diagonal is 0 for any k greater or equal than the sum of dimension plus order minus 1. But we know that it's twice the cohomology of the product of the x times x is different to 0, which implies that there is a non-trivial element of the kernel of this map, and by properties of sectional category this is given. I mean, by the cohomological lower bound is given. So from using this, we can find this sequence, as I was mentioning a while ago, a sequence on the end sphere in which we can see an explicit example on the case that the effective topological complexity is descending from stage 2. In a very simple case, it's set to acting on Sn by involution, and we reproduce the whole sequence of effective TC of Sn with respect to this action. So if you will allow me a couple of minutes to mention the further directions that I think this can be taken, and I apologize for overstepping a bit on the time. So of course, probably the most pressing issue that has to be solved right now on the realm of effective topological complexity is determining when the effective TC of a space is 0. Sorry. it will be interesting to go further into the investigation of the relationship with the orbit projection map. For example, what happens if instead of considering that it's a fibration, we consider this is a branched cover? What kind of, to which point the arguments that we were making here could be readapted, and then to relax even more the possible conditions. The case of branched cover is particularly interesting because many manifolds can be seen actually as a branched cover of certain group actions. So it will open the realm of many computations of effective topological complexities or different manifolds with different interesting group actions. To introduce new variants of effective topological complexity, for example, discrete effective TC, simplicial effective TC, and even more interestingly, I would say, introduce the notion of efficiency into it, like as if it has happened with the efficient topological complexity, or with the recently introduced and investigated geodesic topological complexity. And also studying for example, the topological complexity of maps and of certain maps, like for example, the workspace map and this kind of quite applicable possible derivations of the theory. And the problem of algebraic conditions for effective TC of groups. Like Eilenberg-Ganea determined in the 65 the famous equality in the category of group coincides with the cohomological dimension. Farber asked, what about the case of topological complexity? It's possible to characterize it in purely algebraic terms. And Grant, Meir, and Pachkoria in 2020 introduced this idea of equivariant cohomological dimension to bound the LSG category. I mean, to actually give an analog of Eilenberg-Ganea of the LSG category. And in the very recent survey on the matter of equivariant topological complexities, Grant asked what could be the possibility of finding this algebraic characterization of the different equivariant topological complexities. And also the possible ultimate goal of the whole theory on effective topological complexity would be to classify all possible sequences that could appear as effective topological complexity sequences, but this is surely like a more than tangible problem, like a horizon to strive for. And thank you very much for your attention. And I'm sorry I was a bit overstepping on the time.
That's okay. Thank you very much. If everyone will applaud, that'd be great. That was a nice talk, Arturo. Lots of interesting ideas. Any questions? Actually, I have one that sort of uses two things that you said, but I don't know how they connect. So I'm thinking of a nil manifold, for example. So first of all, the orbit map, you take a nilpotent Lie group and you take the orbit map to the nil manifold, quotient by a discrete finitely generated subgroup. And so that's null homotopic. Now, can you show something about the effective topological complexity of that action of the nilpotent subgroup, the discrete subgroup?
Right, but that will be on the.
See, again, that might be another counterexample to.
Could be actually. I don't know. I will have to think. I will have to.
Okay, and the second thing is, you mentioned about a frame manifold. If a manifold of the frame bundle, if a manifold is parallelizable, then the effective topological complexity, I guess, of what was it, the SON action, or that turns out to be TC of the manifold itself.
Exactly, of the manifold.
So again, a nil manifold, one of the things we'd like to know is TC of a nil manifold. And maybe somehow understanding this business, a nil manifold is parallelizable. So we would like to understand perhaps something with that too.
Right. The thing is that for this you will have to find another approach, right? To actually find
there.
Because it will be like a circular argument in the sense that you know that in terms of the TC of the manifold, but then you will have to find another approach to study the. But no, but nonetheless, it's in.
So think about no manifolds.
Yes. Like bottom line, think about the manifolds in the content. Thank you very much.
Okay, any other questions? Okay, I'm going to stop the recording right now.